Okay, so I'm going to talk about the optimization and discrete mathematics portfolio that I've been associated with for several years. If you'll just go to, you do the slides or I do them? Okay. Next slide then. The focus is on optimization and discrete math, and in particular for large complex problems. These could be thought of as being at the core of many of the things you've heard people talk about, such as Fariba did a minute ago on optimal control. We tend to drill down from the potential applications to the math that really needs the work right now. The sub-areas of the portfolio are listed here. Analysis-based, you can think calculus, more or less traditional optimization. Continuous and discrete search methods have been around for a very long time, first popularized probably in modern times by chemical engineers searching for the right temperature, the right compounds, whatever. More recently, things have moved toward dynamic and stochastic optimization, and at the same time, simulation has gotten merged in there. Years ago, when I was a student, for example, you either solved the problem by optimization or you gave up and simulated. But these things have kind of come together. And then finally, there's combinatorial optimization, which is the world of many choices, many strategies, and generally discrete, such as at any move in a chess game, what should I do? You could think of trying out all the possibilities, playing them out like Deep Blue did, or you could try to do something smarter. So that's a brief overview. I'll just first mention something about optimization research for a few of you may not know, and then I'll talk about the strategies, the goals, and certain applications that have been identified, because as I indicated, what I've tried to do is find applications, future applications primarily, and then work back to figure out what math we should fund. We can't fund everything. The world of applied math, the world of optimization, discrete math is extremely broad, so I've tried to make the selections that way. I'll give you some trends, some transitions, and so forth, and finally some examples. So what goes on here? Wow, it's happening fast. Okay. Well, the idea is you start with some very hard problem, and from that you move on to actually modeling it. So the reason I say this is because in much of science, the model is something that is presumed to exist in nature. And here that is not the case. The model here is in the eye of the beholder, or more particularly the eye of the decision maker or the designer. Once the model is proposed, we go on to establishing the properties of the model: existence, uniqueness of solutions, computational complexity, what approximations might be useful if the problem is too hard, duality theory, and so forth. Once, or in parallel with that, is the development of solution methods, which leads to convergence theory, error analysis, bounding the problem. Remember, it's a hard problem, so it often is not something that's going to yield easily. If you do this successfully, then I use the word generalize. I'm not sure it's the best word, but this model that you proposed right here that might have been to do something in portfolio optimization and financial engineering might later be used in a completely different field because of the success of this model. It might be something that's being used in military logistics. Okay, so that's why the model is so different and so important. Just briefly, and in vector notation, you have some sort of function, and you have constraints, and for the interest of simplicity, we just have one long vector x of unknowns. Many parameters are in here, and as time has gone by, we've started moving more and more from the from the deterministic to the more stochastic and time-dependent problems. If you ever had an introductory OR course or something similar, you probably saw linear programming as the simplest in terms of functional form, and nowadays considered to be a well-solved problem, both theoretically and computationally. It's been estimated that about 25% of all scientific computing time now goes into linear programming, whether it's solving some supply chain problem or whether it's buried down in the middle of a complex optimal control code doing something else. I'll just make a quick comment. This is from a calculus book. You will recall that local optima are a problem in general. Here we have something like a cross-section of a mountain range. We have peaks and valleys. We're in general more interested in global optima than local optima, but this is an issue that until someone solves a $5 million problem is going to be with us for some time. Goals, very simple. As I said, I try to find what the Air Force might be needing that I think something can be done about, and then I drill back down to what the math might need to be, and then I'm trying to find the right person to work on it. Of course, sometimes when you look at this future problem, it could be that the problem the problem is already fairly well solved. I mean, for example, if it looks like this problem in logistics is really a big linear programming problem, then there's no longer any interest, because it has to be not only something for the Air Force, but it also has to be on the cutting edge of optimization research. So what I've been doing is stressing rigor in both the models and the algorithms, especially with the rapidly evolving data and uncertainty in the data. I've tried to engage more recognized optimizations researchers. Two have become members of the National Academy of Engineering in the years I've been here. I think that brings our total to 4, if I remember right. And I've also put some emphasis on young PIs. And I've tried to foster the collaborations listed here, some with a little more success than others. This is just a short list and very partial list of the things that I've been able to identify. There is some need in engineering design for work on the underlying theory when you get to petascale computing. We funded some of that. Actually, we're not funding it right now. I'm also quite interested in risk management, because too often people who try to put risk into models are using some fairly simple concepts that go back a long way to just dealing with averages, or maybe averages plus a weighted standard deviation, and there's much more sophistication there now, primarily coming out of financial engineering. And then in the game theory area, I'm going to show you in a minute, I think Tristan yesterday and Fariba earlier today mentioned attack-defend models. It's really kind of surprising to me how much Stackelberg games, which I've been working on in my own work for some years, has come to the fore. But you have to remember that the underlying domain of the mathematics can be different. One can be in the differential game theory, where the models are, where the equations are partial differential equations, or it can be more in the dynamic programming area where things are indexed by time, or it can be just static data. Real-time logistics. Air Force is doing a lot in logistics now, and we're trying to look toward taking all logistics algorithms and moving them toward real-time solving them very quickly online. I'll show you a little bit about optimization in learning and its relation to machine learning, and so forth. There's something here I've got on a later slide on metamaterials, and so on. I'll get to those. But my point is that these are some that I have identified, and even this list is not complete. Scientific challenges, we're usually asked to say that. I've got the list here. I think non-differentiable optimization, getting away from derivatives. Almost any time you see engineers or scientists working on an algorithm, they will talk about some method to approximate a gradient. I'm hoping that one day that can be relaxed actually, the Air Force has been involved probably more with AFOSR has probably been more involved with non-differentiable optimization than they realize. As you'll see shortly, a lot of the combinatorial problems are actually being addressed with continuous methods, which I think is a nice frontier, not entirely new, but a frontier. Simulation optimization, the interplay there, you'll see. We're doing some work in the whenever these biological and social networks are put together, it's often a fundamental problem is to find some substructure within the network of specific time. Just think of a maximum clique or something like that. And we have PIs working on that. I mentioned logistics. Fareeb and I want to bring some of this notion of risk and uncertainty that has been motivated mostly by financial engineering into the world of engineering design. Engineering designers, by and large, tend to use rather old techniques for when they put uncertainty into their design considerations, and we'd like to bring that up. I mean, if you just think nuclear power plants, of course, they don't do that. They go to the far extreme of what is the worst case that can possibly happen here. But there's a world in between shooting for the average case and shooting for the extreme case. And so we're doing some things there. And in terms of potential impacts, I'd like to think we may have an impact on, the math may have an impact on metamaterial design, engineering optimization, and these other things listed here. Just a short list. Trends, again, think calculus here. The traditional optimization, this is in a fixed budget of the last couple of years. This has been going down a little bit. These two at the top are the traditional ones. Search-based things, whether continuous or discrete, still doing this, but slight downward trend and slight upward trends in the, I don't know whether, okay, new algorithm. So the dynamic, stochastic, and simulation optimization, more emphasis there and more emphasis on the combinatorial optimization, as you will see. Okay, I'm going to give you a couple of transitions first instead of at the end. This is one, I apologize, I've used it every year, but it's such a good one, I can't resist. And besides, they keep sending me new transitions, so I've got usually something new. It's got a little bit of everything in it. First of all, John Dennis, this is not being funded anymore. John Dennis, now retired, prominent optimizer. Charles O'Day at École Polytechnique in Montreal, and Mark Abramson, who was at AFIT. It says Boeing, and that's where he is now, but at the time, so we had international component, prominent professor, and someone from AFIT. So that's good, all of that. And furthermore, they made the first use of a theoretical construct of Clark derivatives in the development of their model adaptive direct search algorithm. They've got significant speed ups, and they had a series of publications in one of the top journals. So, you know, just going across the top and down the left side, you've got a pretty good results of the project. To give you an example, this is a detoxification process design problem, and conveniently it's only got a couple of independent variables, which are chemical concentrations down here. This is the landscape of this problem. I'll be using the term landscape a lot. This is the landscape. You can think of it as a mountain range, and the right two combinations of these chemicals are needed to find the maximum wherever it is, up in here somewhere. It's a little hard to tell because it's projected onto this slide, onto the plane. But searching for the global maximum here, before this particular problem, which was solved by this MADS algorithm, came into being, they were basically running a simulation overnight. They would set parameters, go home, come back the next day, and see what happened. Okay? You will also notice that this thing is very non-smooth, so this is why derivatives may not be the way to go. Not going to dwell on this because I've talked about it in past times. It's been used now in helicopter design, airfoil design. This is actually surgical design to increase blood flow. I think it's called Fontan surgery. It's a surgery they do on infants. But here you're just trying to redesign, decide exactly how to redesign arterial system. And the last thing that I got from them had to do with estimating how much water you're going you're going to get out of the snow in Quebec. Of course, there's a lot, but the question is how much, because Hydro-Quebec uses that water to generate electric power, and if they need to get other sources, they would know. Here's a newer application, and it relates to the attack-defend models, but this one is a little more concrete, perhaps, than, and it also has the additional, not just defend, attack. Defend means, we read this right to left. First, you defend whatever you're defending, in this case, this network of San Francisco roads, San Francisco Bay Area roads. Then you have an attacker who goes after this in some way. And the scenario here for this prototype model was that one or more bad guys would do something like turn over an 18-wheeler and set it on, or an oil tanker on a bridge and set it on fire to disrupt things. This is not a nuclear attack, which would take care of everything, I guess. But and then finally, so you have some resources with which you defend. Then the attackers attack, and they know what you've done, and then you come back and defend, or better yet, you operate. In other words, you get back operational. So that's the kind of thing. You're under attack, or you defend, you use your resources to prepare, you get attacked, and then you come back and try to get operational as well as possible with additional resources. So the critical arcs are what you want to defend. The attack is, in this prototype, is to impede flows. And in transportation world, by the way, the underlying transportation problem here is a big Nash equilibrium game, because the idea is, and accepted in transportation, is that the users of this network are going to find themselves in some sort of equilibrium. They can't be made to jointly optimize flow over the network. They're going to each try to optimize their own situation. This is well known to be a Nash equilibrium problem. It has a solution and so forth and so on. And then you operate after the attack. So this is formulated as a nonlinear defend, attack, defend model, and it is an extended Stackelberg game because Stackelberg only went this far, defend, attack. Now another layer has been added, and it's big. So this study was done, and it led to some new, good nonlinear decomposition algorithms. As I said, we tend to focus on that part, the math. The equations would be just too much to put here. I don't do that in talks of this sort. And the model, this particular model, again a prototype, allowed a relative importance of the different components. It was surprising to some that some of the roads were more important than some of the bridges, for example. Okay. There were some improvements on standard risk analysis by doing it this way, and there were some cost assessments of the cost of defending versus the cost, the economic loss, and all of that. So this was kind of a prototype to prove that they could do this on a problem of reasonable size and nonlinear and with an underlying Nash. So just the fact that it's a Stackelberg game doesn't mean there can't be a Nash equilibrium, which is another game going on underneath. Big complicated problem. So the transition I want to tell you about is very recent. They took the exact model, modeling concept I should say, but different data for Vandenberg Air Force Base and the electric power system there. And this is deliberately kind of fuzzy because I'm not supposed to go into this report in any detail, but I can tell you that it exists and it's been given to them. But the basic idea is to then say, okay, for this particular electric power network, how should we harden it if there are these small groups that might attack it? So that's a pretty good transition because it is a, I think, government-only report that's available, okay? And I asked them what was the reaction. They said, well, the commanding officer has not responded yet, but the people that run the network were dubious that this was needed because they know they have excess power. But that's not the point. The point is, can you break this thing up by hitting couple of key points, and there were even some points outside the gates, I understand, that were fairly critical here. So I think this also feeds the California power grid. Some interaction with NSF, ONR, and I don't have anything joint with ARO, but one of the PIs does, and one of the PIs also have additional funding from DOE. And the international collaboration, I mentioned Charles O'Day. I have 2 people here at Waterloo, and Jim Fillerup mentioned last week the work of Claudia Sagastizabal. Getting her on board was a really good thing. She is a super talent, and what happens is she works with Bob Mifflin at Washington State on something near and dear to my heart, which is a non-differentiable optimization. So here are some examples from the portfolio. I'll go through each of those areas and say a little about each. Discrete search, theory and methods. These are some people: Sheldon Jacobson at Illinois, Howe and Whitley at Colorado State, and they are working on what to do about these landscapes, and like the one I showed you, and how to search them. These problems all fall into the NP, complete NP hard categories, but these are the hard problems that come out of difficult scheduling, routing, and so forth and so on, fleet management. The group at Colorado State, this little graphic, looks like it's got a mistake in it. I've been using it for some time. They got into this because of the scheduling of a limited number of radar tracking objects in space. But this was kind of the motivation at the time, but this quickly led to studies of landscapes. You can have landscapes like the one I mentioned before, or you can have something that's smoother with still all the local global optima problems. Key result they have here, I guess many of you heard about the traveling salesman problem. It is a certain combinatorial problem of routing through a network and coming back, going only once to the nodes of the network. It's a celebrated problem because it's known that if you can make a dent in this problem, you can have an impact on all the problems in the NP complete class. And in fact, a few years ago, there was an 800-page book published on just this one problem. There are specific instances. They're up to 15,000, 20,000 cities, which seems incredible. But that's specific cases, not the general case. But work on this would impact supply chain, logistics, circuit design, vehicle routing. What they came up with is something called a crossover technique. Can't go into details, of course, but it's a fairly straightforward way of moving from one local optima, or taking 2 different local optima and making the next move. They prove that this can be done quickly, in order, in time, and they also are getting very good computational results out of this, because that's where you have to go to prove that what you're doing works. Jacobson is working on dynamic asset allocation, whether you're loading an aircraft, whether you're deciding how to use various facilities in screening people in an airport, or whether you're doing general scheduling problems in a manufacturing facility or anywhere else. The main thing that I like about his work is that he has theoretical results on what happens if the data is deficient. Where you don't, in other words, traditionally people say, well, I've got all this data, now I've got to make this decision. And we're trying to get away from that, more toward evolving data, incomplete data, and stochastic data. So he's made some progress there. Quantifying rigorously what it means to be deficient in the data and what implication it has for solving the problem. Analysis-based, the more calculus-based things, I've got 2 or 3 things here. This is the non-differentiable, I'll show you in a second. And then with help from others, we got into material design. Oh, and then there's this work on, I'm not going to talk about this. There's some fairly nice work. This is now moved over to Bob Bonneau's portfolio, but it's work wireless network operation. Frequent got some nice results on maximizing flow through the network. But let me do these others. I gave this last year. I wish the convergence of the research was as fast as it was superlinear, but it's not. But they are making some progress. It was conjectured about 25, 30 years ago by a famous French mathematician that this could never be done. The question is, when you do not have derivatives, is there a way to still get superlinear convergence? Probably everyone knows that if you can use Newton's method, which not only requires first derivatives, requires second derivatives, you can get quadratic convergence, which is a special case of superlinear convergence. But if you can get better than linear convergence, you feel like you've won the game. In any case, they have shown for certain classes, fairly broad classes of convex problems, that even when the derivatives do not exist, you can go from linear convergence. You can't read this, but this is error in the solution of the problem, and this is going from like, I think that's about 10 to the minus 4 or something, down to 10 to the minus 16th. It'd be double precision accuracy. So this is going at linear convergence. These are two variations which are Newton and quasi-Newton variations, not real Newton and quasi-Newton because the derivatives aren't there, but their method. The iterates of their method are shown over here. You're converging through some two-dimensional space, in this case, from one point to another, making lots of different kinds of steps. So the issue is, how fast can you move from here to here to here and in the limit get to the solution? That's what you want to do at a superlinear rate. So I have hope that, and there's another project being funded that now that I'll have up here, that engineering designers will make use of these methods, or there will be routine to use these methods rather than gradient methods. The application that I mentioned about band gap optimization, here again, I'm not a materials scientist, and I only partially understand where this problem came from. But the idea is that this has to do with the design of materials, can give very precise control of light. It's been known, I guess, for a long, long time that it should be possible to do some band gap optimization with these crystalline structures. But what interested me was this area of semi-definite optimization, which has come to the fore in recent years. Could be a good way to handle design parameters. So this work by this group at MIT got published about a year ago in a computational physics journal. The part I'm focusing on was the use of the semi-definite programming, and a key ingredient here was to somehow break this problem up into the right subspaces and optimize over those subspaces. The results claimed that they have very large absolute band gaps, multiple complete band gaps, and I guess the paper got published because all those claims were basically true. Now the problem is a lot of these structures are not going to be something you could fabricate, not yet. We're hoping that will happen someday. Some of these things are kind of, you know, they're sort of suspended out there with nothing around, no connectivity. There are lots of little jagged edges that at the nanoscale that no one could design yet. But some progress has been made here. In the dynamic and stochastic area, I'll show you a couple of things. First, I'll just mention what is the problem. This is a very generic statement of the problem. We're moving through time. We've got some sort of cost function. We've got some sort of discounting. And we're moving from state to state, from state ST to some other state. X is going to be a reflection of where we are. But the critical thing is that what we're doing in these problems is trying to find the right policy for moving through this system, moving through time. And there is some system model. Again, this is very generic. And of course, there's randomness in this system. So this includes a lot of things, as you'll see in a moment. But I mean, these are very hard problems because they're very big. There's a lot of uncertainty in them. But the idea is to get down to good solution techniques, provably good solution techniques with a minimum of tunable parameters. I borrowed a slide from one of my PIs. He said, you know, it's just a jungle, because there's so many people from so many fields working on this, and but I'm happy to say they're starting to overlap and talk the same language enough that things can be done. For example, this is Warren Powell. He is using a concept that I think first came out of machine learning, a fairly simple concept called the knowledge gradient. And it's a certain way of, as you're doing a series of things, of making your next move not just to get better, but also to gain more information. Because you know you're going to have to make another move, and you're going to have to use so you're trying to accumulate, not only are you trying to make your objective function bigger, like in those landscapes, but you're also trying to gain additional information so that the next move will itself be better. And he has been doing this, and I would say, even though the idea came from some other fields, the theory of what could be proven about this is pretty much due to him. And right here, I think, if I remember right, they were doing some drug design, and I think they would have like hundreds of thousands of possibilities, and they were able to get optimal design in like a few hundred experiments. So they reduced it by, you know, the total, from doing, say, total enumeration of several hundred thousand possible combinations, they got it down to maybe a few hundred combinations to get the optimum. I mentioned this last year, and this is a connection between the simulation and optimization. Here's a simple one variable problem you would like to optimize, difficult because of all the local optima. The global maximum is here. What you can do in this theory is you can treat the iterates here as if they came from a distribution, and that's what the top plot is. You do one experiment, well, you get one function value here, you construct a distribution. You get another value, you construct another distribution, and so forth. And what's interesting about this is, despite this global local issue, what's nice about this is you can actually prove that in the limit that this process will converge to a point mass at the global optimum. The problem with this is it's limited to rather small scale problems. But we've got a new YIP a proposal that was funded that I think may make a dent there. Logistics I've mentioned. I don't have too much to say here. It's a very big dollar item in the military, of course. These people have taken some of the key problems. I don't have the word lot sizing here, but critical lot sizing problems that are the fundamental of supply chains, and develop methodologies for, provably good methodologies for doing this in real time. And we did have a workshop in 2010. We weren't able to do it in 2011, but maybe we'll get another one in this year. In this same area of uncertainty and decision making, I like these results from Cassandras at Boston University. This is just a little schematic to say you've got some vehicles that are searching for events in an area. There's some sort of uncertainty. The question he asked is, do we need the things that are searching this space for the events being bombs, landmines, bad guys, whatever, is the communication among the agents here, should it be synchronous or asynchronous? And in some very nice theoretical work, he proved, see, the synchronous communication, this says number of communications here, over time, number of communications goes up essentially linearly in this in the synchronous case, but it's much, much slower growth in the asynchronous cases, properly defined asynchronous cases, and yet you still get optimality with less communication. So he just stepped back and looked at the general problem of agents searching an unknown space and addressed the issue of how they might communicate. Now in my last 5 minutes, I guess, I'll talk about combinatorial optimization. Again, the issue is identifying substructures in networks. Networks are nodes, which may be agents, links, or interactions. It all depends on what you're talking about. Social networks, it doesn't really matter. It could be biological networks. Key concept is a clique, a subnetwork that's totally connected. A K-club is a generalization of that. I'll show you a couple of pictures in a minute. These applications exist, been used many times, protein interaction, call networks, internet graphs, and so forth. So again, what we do is don't really go after these applications. We try to go after what is the math that is needed to get at these problems. One of the nice results, and this is part of the, I guess, collaboration among PIs, the group at Waterloo didn't even know about, well, the group at Texas A&M, but they kind of were inspired by it. And in certain type, even data mining, this is data mining really, you can just imagine that here there's a clique of, let's call them bad guys, since that's, that are in constant contact with each other. But you see, this data could be contaminated by putting a lot of additional false connections in there. And the question is, can you still find it? And it turns out that Vivasys proved, at first I didn't believe this, because if you know Motzkin-Strauss, which is the standard nonlinear way of solving a clique problem, it's an NP-hard problem. But he found that under certain hypotheses about how the network is obscured, with certain probabilities assigned to these arcs that you're putting in, that he could actually find these cliques with convex optimization. Convex optimization is polynomially solvable. I mentioned this last year. This is a protein-protein interaction for a certain pathogen, and you may be looking for K-clubs within this. Here's the conjecture. A biologist says, I think that these protein interactions are going according to the following rule of thumb, or my theory is, or my conjecture is, and that would then lead to the conclusion that there is a 2-club in the network, or the 2-club is a certain size. 2-club means sort of just what it says. Here it is for yeast. Largest 2-club in yeast is means it's really remarkable that to me it looks like this. In other words, all of these proteins are within one jump from each, or within 2 jumps of each other. You go, in this one, you go from here to the center to another one. And this is a 2-club in that pathogen. This is the 3-club in yeast. It looks sort of like the U.S. airline system. You know, you can get from almost any airport to any other airport in 3 hops, right? Right, Hugh? And finally, oh, only 1 minute. Okay, sorry. Polynomial tiling is something that is being worked on. This problem came to me from R.J. Notchman, which has to do with the design of phased array systems. It was discovered at the census directorate that irregularly packing, in other words, the idea is that the phase shifters on a large phased array antenna, if you put 1 per element, they're too many, it's too expensive, so you can group them. And when you do, if you do a regular grouping of these, like tiling with just rectangles, you get a lot of interference. But they found that if you do it with polyominoes, you get much less interference. This is with 1 per element. This is with regular tiling. This is with polyomino tiling. So we've had a group working on that. And again, I don't have time to go into it, but the details are that nonlinear optimization is used to arrange these things. The question was, rather than just doing this in an ad hoc way, how do you do it mathematically? So one way is to define centers of gravity for these tetranimals here and then maximize the entropy. Maximizing the entropy gives you an irregular tiling, which implies it should be low interference. Minimizing entropy gives you a regular tiling. They're at the level of getting about a 50 by 50 in about an hour on a laptop. 0, 0, okay.